Molecular geometry. What does that give us? A clue that we might be doing. We're looking at the shapes of the molecules, right? Geometry generally deals with shapes. So we're going to look at the shapes of molecules, which is exactly true. Okay? So what molecular geometry does is it allows us to look at the three-dimensional arrangement of the atoms in space, right? We're going to look at what it looks like three-dimensionally. We're not going to have to become like great artists and learn how to draw three-dimensionally, right? That's not what I'm here for. But I do think it's good for us to be able to envision what these things look like in space. And so we're going to use an app next week to kind of be able to build molecules and manipulate molecules and see them and move them around in space so we get a little bit better idea of what these shapes really mean. Okay? So when we look at an object's three-dimensional arrangement or three-dimensional shape, we're going to be able to look at the shape based on that atom's electrons. Okay? We're going to look to the number and to the type of electron domains to figure out what its molecular geometry is. And so domains is a new term for us. Electron domains is a new term. Okay? I'm going to change my definition here just a minute. So electron domains, at its most essential definition, is basically how many things... Go forward. There we go. Okay, too many. How many things are bonded to the central atom? But really what we want to say is how many things surround the central atom. We don't want to say just bonded. Okay, so let's go ahead and change that part of the definition. How many things surround the central atom? Make that the definition instead of bonded to. My iPad's moving a little slow. All right, here we go. How many things surround the central atom? Because domains can contain either lone pairs or they can contain a bond. Okay, so when we talk about electron domains just being things that are bonded, that's really not true, right? It's anything that's surrounding the central atom is going to be considered an electron domain. Okay?
What is that definition of?
This is the definition of an electron domain, right? Electron domains. It's basically how many things are surrounding that central atom. Okay, we're going to dive into this in just a second here. Okay, when we're looking for an object's three-dimensional shape or we're looking for its molecular geometry, it's hard for us to tell its shape just based on the formula, right? Just based on the formula H2O or based on the formula CH4 or whatever it is, it's not easy for us to just look at the molecule and determine the shape. So we're going to use something called this Vesper Theory, which is a way for us to determine the shape of the molecule. Okay. In order for us to determine the shape of the molecule, we're going to use what is called Vesper Theory. And I know that's not really what it says. I know it says VSEPR, but the easiest way for me to say it is Vesper Theory. Okay? Vesper, this is an acronym. VSEPR is an acronym, and it stands for Valence Shell Electron Pair Repulsion Theory. Okay, and that sounds like mumbo jumbo, but go ahead and get it written down, and then I will explain to you how those terms relate, and I think it'll clear up a couple things. So get that written down. You will kind of need to know what that acronym stands for. Okay, so maybe highlight that in your notes, circle it, something, but you are going to have to know what that means. Acronym. The acronym says Valence Shell Electron Pair Repulsion. Okay, so what does it mean when we say valence shell? Are we talking about inner atoms or the outer atoms? Outer atoms, right? We're talking about the valence electrons, so the ones that are outside, on the outside, available for bonding. Then it says electron pair. So what does that include? It includes lone pairs, and what else does it include? Bonds, right? Both bonds and lone pairs are pairs of electrons. Okay, so we're talking about outer shell electrons that are either involved in bonding or in lone pairs. Then what does the word repulsion mean?
It's like,
Is it to come together or to separate? To separate, right? Repulsion is a version of repel, right? So if we're talking about these valence shell electrons repelling from one another, that's exactly what happens, right? What's the charge on electrons? Negative. And do negative and negative things like to come together? No, right? Negative and positive come together. Negative and negative repel one another. And so what's happening in three-dimensional space with these atoms is that if I've got a lone pair and I've got a bond on the same atom, they don't want to be right next to each other. They want to spread themselves out, right? The domain that contains that lone pair and the domain that contains that bond, they don't want to be right next to each other. So what happens in these three-dimensional shapes is that electrons orient themselves as far away from another electron pair as they can, right? And so that's how the shape is formed. Okay. That's what I already said. Okay. If you're going to write down anything, just write down the second bullet of that. Electrons repel each other. They want to be as far apart as possible, right? That's what we're looking at. The pairs of electrons want to be as far apart from another pair as they can. Okay? Repulsion between sets of valence electrons surrounding causes these sets to be far as apart as possible. Okay, so if you're going to write down any part of that, just write down that little block, right? Electrons repel each other. They want to be as far apart as they can be. All right, we mentioned what an electron domain is, right? It's how many things are surrounding the central atom. But we need to remember that there's going to be two types of electron domains, okay? Domains can be considered a bonding domain, and all that means is that that domain contains one or two or three bonds, right? It contains a bond. What do you think the other type of domain is going to be called? Okay, yeah, kind of. That wasn't a very good clue for you. It's just called a non-bonding domain, right? It's even simpler than lone pair, right? It just means that these electrons are not involved in a bond. Okay, so we've got bonding domains and non-bonding domains. Okay, non-bonding domains contain a lone pair. Bonding domains contain at least one bond. Okay, at least one bond. And we'll talk about that here in a second. They contain at least one bond. Okay, this bonding domain, where it says contains a bond, you could even put there contains at least one bond. Okay.
Did you say at least one lone pair? Or
this one is just a single lone pair. But when I say a bonding domain contains at least one bond, this is what I mean. If I have carbon double bonded to oxygen, and let's say, I don't know, single bonded to something else over here, right? Let's say this is part of a Lewis structure. This would be considered one bonding domain, even though it contains a double bond. Does that make sense? And then this is another bonding domain. So that carbon would have two bonding domains. Okay, two total domains would be happening there. Okay, very good. Let's look at water. I have the Lewis structure for water up here. How many total electron domains are on our central atom? 4, right? Let's identify those domains. Okay, so we've got 4 total domains. 1, 2, 3, 4, right? Because these, it's not like we can count like this as a single domain because they're going to 2 separate atoms, right? So we've got to have a bond right there, a bond right there. So this has 4 total domains, okay? Second part, how many of them are bonding domains? 2 of them. 2 of them are bonding domains, and how many are non-bonding domains? 2, right? If I'm going to identify them, I would say that these lone pairs up here at the top, right, they are going to be our non-bonding domains, and then our bonded hydrogen atoms, right, those are going to be our bonding domains. So I want you to take out the molecular geometry handout that I gave you, And I want you to start looking at how we identify the geometry of this molecule, right? We're going to start with water. So the first question that I ask you to look at on that molecular geometry handout, we read this graph or this chart, not a graph. We read this chart by finding where the two things we want intersect, okay? So this column says how many total electron domains does your central atom have? That's what we're looking for here on our molecular geometry sheet. So in this example, how many total electron domains does this oxygen have? Okay, it has 4 total domains. So you're going to be looking on here, 4 total domains. These are the possibilities for my shape. Okay, just the ones in that row. So then I come up here and I look at the top. Does the central atom have no lone pairs? No. Does it have 1 lone pair? No. Does it have 2 lone pairs? Yes. So I'm going to come down here and I'm going to find the intersection where 4 total domains, 2 of those are lone pairs. That means the shape of this molecule is bent. Right? That's what the shape is called. Bent. And it just so happens that it looks exactly like that one. Right? What questions do we have about how we use this chart? Okay, whenever we're asked to find a molecular geometry, you have to draw the Lewis structure first, because otherwise you don't know, well, how many domains are there and how many have lone pairs and all that kind of stuff. So, BCl3, boron gives us 3, chlorine gives us 21, so that gives me a total of 24 electrons. What's my central atom here? Boron, chlorine, chlorine, chlorine. What do we know about boron? Do you remember? Right. It's okay with not a full octet, right? It only gives 3, so it's okay with only having 3 bonds. Okay, so I've used 6 of my electrons. I have 18 left. Where does it make sense for those 18 to go? Right. Finish our octets around chlorine, and that's going to finish all of our 18. And we're okay. Boron is okay with not having a complete octet. Now we're going to look to our sheet. We're going to say, how many total domains does boron have? It has 3 total domains. Okay, it has 3 domains right here. 1, 2, 3. Does this boron contain any lone pairs? No. Does boron contain any lone pairs? No. We're only looking at central atom. We don't look at what's happening on the outside. We look at the central atom. Boron has 0 lone pairs. So we're going to come to the part of our table where those things intersect. 3 total domains, no lone pairs. What's it called? Good. Trigonal planar. Okay, so trigonal planar means that it's just a triangle. And they all sit in the same plane. Right? With only 3 things that want to spread out, they don't have to really stretch 3-dimensionally. They can just orient themselves 120 degrees apart. That's where that angle comes from on your sheet there. Trigonal planar 120 degrees. That means that this bond is 120 degrees away from that bond. And that's 120 degrees away from that one. And it's 120 degrees away from that one. Right? That's the farthest that they can possibly orient themselves, and so that's how they did it. Right? There's no need for it to become like out of the plane, right? 3-dimensional. It's okay with just being a flat little triangle. That's why it's called trigonal planar. Right? Okay, what questions do we have about that? Trigonal planar would be our molecular geometry. Okay, so if I'm looking to draw my Lewis structure, we have to start with our Lewis structure every time. It's got to be drawn every time. 1, 2, 3, 4. That gives me 8 electrons that I've used, which leaves me with 24. So we've got 24 electrons. We've got 4 outer atoms that don't have complete octets. Does that add up? Yeah. 24 divided by 4 would be 6 electrons each. That's what we want. Okay, so now we've used all of our electrons. We've got none left. That's my Lewis structure for CBr4. Now I want to know my molecular geometry. Okay. I'm going to look to carbon only. Carbon only. Let's see how many domains in total does carbon have. 1, 2, 3, 4. Okay, it has 4 domains. How many lone pairs does carbon have? 0 lone pairs. And so if I look at my chart, the place at which those two intersect is called what shape? Tetrahedral. Tetrahedral. Okay? And what that looks like is kind of a little pyramid, like a little triangle on the bottom, and then the central atom is pulled up a little bit to make it three-dimensional, and then that last one kind of sits on top. So it almost looks like a tall, skinny pyramid, right? That's kind of what the tetrahedral shape looks like. If you were going to put sides on it, that's what it would look like. We're going to see those shapes in 3D when we come back on Monday.